Hi, my name is PG Madhavan. Call me PG. Uh, this is a deck that I had published on LinkedIn, but um, talking through it perhaps would be useful. So, in the next 30 minutes, I would like to elaborate on some of the key topics. It's more than just a definition of a digital twin in this conversation. I want to touch upon how it is related to digital transformation that many enterprises are going through today. And to me, there is a one-to-one correspondence. And to achieve the value proposition, the true value proposition of digital twins, that is performance improvement, there is a need for something called causal machine learning. And it is very much less known, but all the pieces are in place and it's ready to get deployed and really make a difference in the value digital twins can deliver. So my journey in this started back in 2000 when I joined Rockwell Automation and had the chance to lead the development and deployment of the first large industrial scale IoT system, along with what we now call a display digital twin. And it has stayed with me all this time, including the business lessons that I learned, um, which I will recount briefly. The other thread of the story is my experience at NEC. NEC Labs had research and development done 5, 10 years ago in causality. And I had the privilege of taking that and spinning out a company in causality. So these two threads are coming together in my current work in digital twin. So when I go back to my history, as I mentioned, this is a picture actually from the Rockwell digital twin display, digital twin. This is the picture of a typical plant floor where these are the points that we monitor, and our display digital twin will show the current status by green, red, or yellow. And the beautiful thing was when it is red, naturally the plant engineer would want to click on it. And the first thing that'll pop up is a spreadsheet, which is a historical information about that. In this case, it looks like a motor or a pump and this bearing vibration being monitored. So you can see its serial number, when it was installed, vibration data from the last few months, and so on. And then you can now double click on it and actually get real-time vibration data, vibration spectrum, temperature on your screen. One of our deployment was in China, and we could monitor it from United States. But these are early internet days, but it still worked. So before I got to Rockwell Automation, the status of their digital twin, as you would call it, was this gray box here. And I still call it a digital twin because it is a digital model. It was the spreadsheet that is updated frequently with data. So it fits the definition of a digital twin. A person would walk around the plant and then with a handheld measure these vibration and temperature. And at the end of the day, come to a PC, download it. It all comes back to our servers. And then the spreadsheet that you can then call up will get populated. And people got value out of it. When I got there, I said, no, we had to move to the next level. And that's how this thing happened. But things have changed from those days. That was basically for condition monitoring and maybe predictive maintenance. I found from my business relationship with the steel plants and the paper plants and automotive manufacturing floors that initially that was exciting, but that wasn't enough. It was not delivering the value they wanted, which was really performance improvement. So as a very simple starting definition, we can simply say that digital twins are just a virtual working representation, emphasis on working, so it's updated. Here, it was probably updated once a week or once a month. Now, today, it is continuously connected, so it's updated every day, every minute, every hour, etc. So the real-time aspect really varies. And it goes from one piece of machinery to a plant to a smart city. So it's not for just for one small machinery. I tend to think of digital twins in a more relaxed fashion, because this tells you what a digital twin does as opposed to what it is. Essentially, what digital twin does is to take data from these local sensors. So this is, let's go back to that picture you saw on that motor and pump. These are specific sensors, and the data is being collected. And you collect the data in the central or servers, and then we had to create an overall picture. So this is where I likened this to a human syndrome called, this is a problem with the eye that you can only see like you're looking through a straw. So when you have that kind of situation, you're only seeing little pictures of reality or the plant floor of the machine. They have to be integrated to see the full picture so that you can make some decisions on performance, root cause analysis, etc. So once a global picture is created within the digital twin, I'm leaving it completely flexible here. Could be any way of combining this. Later on, we'll talk about a very specific one in the case of causality, but any of them should fit in with this. Now, the whole idea of doing that is now there is a global goal that the person who deployed this millions of dollars worth of IoT, it is reducing waste, increasing profitability, the quality of the product, so on. So then from that, you will be able to, the digital twin should be able to say, these are the local actions to be performed, and have that done so that over time you can monitor it and see that you're indeed proceeding the way you want it. Now, if you want to get more in detail, this is probably much more of a detailed diagram, which I won't go through, except emphasize the point that from the real world, nowadays, anything digital can be part of a digital twin. So it could be video, audio. It need not even be continuous signals. It could be something like transaction logs from a retail store. I had a startup where we were using that and within this configuration. So all those digital information, now we have excellent in Azure and AWS, especially platforms to bring the data, lots of wireless connectivity options. Sensors are getting better. But once you get the data, there are three fundamental functions to perform in a digital twin. That is condition monitoring we talked about, typically close the loop by visualization. So, just like that display digital twin that you saw, but could be through AR, VR. In the case of building, 3D rendering may be very important. But there is this other for root cause analysis and performance improvement where digital twin is lagging, and that is where our value delivery to the end customer is not where it needs to be today, in my personal opinion. So why are we doing digital twin? It is to really extract the dynamic information while it is operating, right? So that you can monitor the condition over time, and through whatever tools that we provide to the customer, the performance can be improved. So there are two major aims: performance understanding and performance improvement. The other ones of just monitoring, etc., is there, but these are the higher level value that a digital twin. This is why people do digital twin, or going forward, that's what it should be. And what is required in that is the data that comes into a digital twin is just data. They're just bits and pieces or bits and bytes. It is the relationships among the data that actually tells the story. That tells you the opportunity to improve performance or why something failed. So that is the place where digital twins of today, yesterday is lagging, but tomorrow, I think we know how to get there, and I want to tell you that story. Now, when you hear this, you will sense that this sounds a lot like what is a big buzzword in all kinds of enterprise improvements called digital transformation. And I'll show the next slide why there is a one-to-one mapping between the two, because I believe digital twin is a great framework to effect digital transformation in enterprises. So if you boil down, digital transformation applies to business plans, and how you address various markets, how you actually operate your existing plant, all of that. But the essence is this: you want to continuously assess. In olden days, say you would set out some operational policies, and then it's like what I call fire and forget. You don't have an opportunity to get continuous feedback. But now with the digital technology, we do. So you're able to continuously assess. And from that, we have to surface information that the operator can then make decisions to or find opportunities to improve their operations. Now that won't be like every day and continuous. It'll be periodic. So these are the two key essence of digital transformation. To me, in this table, as I'm showing it, it just perfectly maps to that. So these two things map to various pieces of that digital twin definition slide that I showed. The first one here, continuous assessment, we are almost there. Visualization, we are there. Where we are falling behind, we have fallen behind in digital twin technology suppliers is in root cause analysis and what if analysis. And I want to solve that problem and move forward. And I'll show you how we can do that today. Now, this is, like I said, not a very narrow thing. I see it as very broad, applicable to a very large number of verticals. But essentially, the idea is what's shown here on the right. It is a virtuous cycle of monitoring, extracting intelligence, engaging with the business system through ERPs, and then closing the loop either through a human interaction and maybe robots later, and ultimately directly if it is an industrial plant, through the PLC, the flow control systems, so that the loop is almost fully automated. So in manufacturing, how it can be used is pretty clear. I'll take just a couple of examples. In electric vehicle, you're continuously monitoring data from the current draw of the battery, the torque from the motor, RPM, etc. There must be a way to bring the information together. Remember that global picture. All that local data comes to a global in-car system, a digital twin, where you can find the relationships and find out how you can maximize the range, because that is a major concern in EV, while it is operating in real time. In health tech, there is a great push to trying to lengthen health span to equal lifespan. Wouldn't it be nice? You're healthy till we die. So all kinds of monitoring systems that you wear on your wrist. And when you go into the hospital, and if you're in ICU, you're connected. All those continuous data stream is coming. Again, you can think of it as a patient digital twin, and one can carry that through to the geriatric years when there is a home healthcare requirement is there, and you have a whole patient digital twin to carry you through. In ag tech and buildings, they're going to be supremely important. In ag tech, by monitoring the moisture level and fertilizer level, satellite data of the weather, etc., you can minimize water use and fertilizer use, which is important for sustainable agriculture. In a building, minimizing, monitoring the HVAC system, the temperature in the rooms, the lighting, electricity. You can reduce the consumption of carbon emitting sources and make it more green infrastructure, and many, many more applications. So how does it usually get deployed? So a digital twin solution, I've done this multiple times, and this is my favorite way of doing this. It always starts with the domain expert. In each vertical, there will be no horizontal technology company, digital twin company, who will know enough about the domain expertise. Think of it as a medical situation like the ICU thing I talked about. Of course, you have to rely on the doctor. If you're on the plant floor, you'll actually see that there are persons who worked on that plant for 20 years, 50 years, 30 years, who just from a noise that is being made can tell you exactly what's wrong with the machine and what needs to be done. So those are extremely important pieces of information. So to me, digital twin solution starts with the domain expert. And there are two ways to abstract and use that information. I'm a big believer in taking their knowledge And I have actually a template, and this is like the old expert system. You walk through it and create a tree, and each branch you uh, give a reason for those branching. So that set of rules, if then else rules, becomes rules engine. Now, in the present day, with all our machine learning tools, directly from the data being recorded, maybe heart rate, respiration, this, that, we can also judge those situations and create useful outputs. So one of the purpose here doing that is most of the time domain experts are little apprehensive about this machine learning thing, which they come and it's going to displace us type of stuff. So there is a confidence building exercise. So if you have the results of these two side by side, there may be mismatches, which may in fact help us improve the machine learning, or it may be the other way where the doctor may think, oh, it's telling me something that I didn't think of. Now, that's a big win. Suddenly, she is now invested in our machine learning solution. So let them continuously judge it and see how each can be improved. And soon, our machine learning would be very effective. It can learn from the data, so it's doing it continuously, not a one-time learning. And we can do predictive analytics, and we'll talk about that in a bit. The other part, which is new here, is the domain expert also knows a lot about what causes what. When there is a smell of smoke from a motor, let us say, when that's a little drastic. So let's say a little higher pitch noise, just by looking at it, he may be able to say, well, I think the shaft is a bit misaligned. So shaft is one node in the causal graph, and then the other is a bearing. The third is maybe electricity draw. So he or she will be able to tell you how to connect these things. So you can get an initial guess of the causal graph from the domain expert. Now, we have methods where directly from the data, we can estimate the graph, we can discover the graph, and then compare with the domain expert's opinion, and then improve both sides, as we did in the other case. And then we can estimate the causal links and strengths between them. Maybe when the motor was fresh and new, the causal link between the shaft and the bearing was like negligible, zero. And now when you measure it, it has become a significant number, which means something this is causing vibration from the shaft is causing, sending energy to the bearing and making the bearing, in a race, rip up or something of that kind. So very specific information. That is going to lead us to some very interesting things, which I will talk about. And typically, just to talk about an actual deployment, there are plenty of excellent IoT, platforms available: Azure, AWS, so many smaller startups and others. So basically, there is two modes of operations. There is an event-driven operation and an on-demand operation. So typically, as the data comes in, when it is continuously measured once a day, whatever, when the data comes in, that is event-driven. Then you would call the display digital twin, of course, so that you can see the dashboard, and also perhaps use the predictive digital twin to say what should be done, or would it fail in the next week? Those kind of things could be displayed. Now, causal digital twin, or the prescriptive analytics part, is a higher level value analysis. It's usually on demand. This is not something you would do, performance improvement is not something you do constantly. This is something every quarter, every month, you review the results, or if it is for root cause analysis, it's when a failure happens. So it is on demand. So two modes of operations for these digital twins. So what do they look like? So let's look at the digital twin setup. So there is, I call it the digital twin ladder. So there are three steps here, and they are built on each other. So I call it a nested Russian doll. So they're all inside each other. So they're not separate things. You need one for the other. So starting from yesterday, this is in late 1990s when I was at Rockwell. This was the digital model. We had a spreadsheet and data occasionally. That's there. But now we are in this segment. We have display digital twins that is primarily useful for condition assessment. predictive digital twin that is primarily useful for statistical projections, such as there is certain percentage probability of failure in next month. So what should we do about it? Those kind of discussions. But if you want to get to really how can we improve the performance of a machine, of a system, of a plant, of a bigger aggregate, you need cause-effect relationship. And I'll explain why. So what it does in this prescriptive digital twin is it is driven by causality, cause-effect relationship between various nodes, as I talked about. And it essentially reduces your complex natural production system into a mechanism where we can tweak the knobs and see, what is the outcome. So you can do outcome analysis. Similarly, when there's a problem failure, you can do root cause analysis. So this is the value of this ladder of digital twins. So the first two is pretty well known. So I'll spend the next 10 minutes just talking about the causal digital twin. The usual joke, of course, or not joke, everyone tells you correlation is not causation. That is great. But this is my favorite picture. This guy thinks he's really moving the truck, but that's just correlated. It's causation. This guy is really the one who's causing this to move. But this is a curious thing. So this causation, so this guy pushing, so this guy creates the thing, the movement. So causation actually implies correlation. So there is no causation without correlation, right? Because if he's causing it and is moving, he will also be correlated to the movement. But there is correlation without causation, like this guy standing on the truck bed, right? It's correlated, but there is no causation. So what we want to identify is things like this in the interconnected or parts of a machine or a plant and so on, and identify more importantly these guys and what is the actual causal effect or factor. Then you put them all together, you get this big graph, and then you can start manipulating it to find out outcomes and find root causes. So essentially, causality is a time immemorial from our hunter-gatherer time. People have always observed, if I do this, this happens. Then they can repeat it. Then they can do tweaks on it. I can talk about an example of hunter-gatherer first throwing a stone and killing an animal, so he has a meal. But then he figures the essential cause effect. Then now he thinks, oh, I can also do it with a spear. It's more effective. So this is the value of cause and effect and causality in general. In 1700s, there were significant discussions and philosophical debates about it. But coming to today's time, there's some work in econometrics, which led to Nobel Prize in 2004 and 2022. But I'll stay with a certain type of causality that is built around directed acyclic graphs, DAG. So basically graphs. So this work was started in 2000 by two eminent gentlemen named Spreadsheets and Pearl. And there is a lot of confusion because causality is built on a lot of assumptions, like any scientific theory is. So it's built on a lot of assumptions. So it applies in certain cases, it doesn't apply in certain cases. Some of the causality estimation and discovery methods applies to one type of data that is like panel data, like market research data. And very few apply to things that are measured and continuously, like sensor data, like we IoT folks are mostly exposed to. So there are, you talk about this and I see a lot of confusion about it. So I'm going to narrow it down from this general in the next slide to very specific for our use case in IoT. So the idea, as I said, is always to find its underlying data generating mechanism. Because once you have a mechanism, you can think of it is very repeatable, right? That is the key. Now you can twiddle the knobs and see, performance improves or something goes bad, and without touching the actual data. So this is all done in your simulations, right? So once the data is collected, you're not going back. In the olden days, the way to establish causality is like a classic example is if you go to your family doctor and you have fever and she says, take this pill, she gives you a prescription, let me use that word, saying take this pill and your fever will go down. She's able to say that, able to prescribe that because someone many years before, some big pharma company has done what is called randomized control trials. So randomized control trials is the gold standard of causality, cause effect determination. But there you have to have placebo and you have to have a controlled group of people with various levels of dosage of medicine, etc. Think of plant machinery. You can't do that kind of intervention analysis. RCT, random control trials, is almost never possible in an industrial and enterprise type of setting. You can't do statistical experiments effectively. And most of the time, not at all. And in some human and other cases, it's unethical to do certain of these things. So what has happened since 2000 is that just from observational data, without experimental interventions, you are able to assess the causal relationships. And based on that, you can do what is called counterfactual experiments, which we will come to. So once you have a causal digital twin and causal model, you can do outcome analysis, as mentioned here, and root cause analysis. So that is what's going to take us to the top of this pyramid of performance. This fault detection, which, as we said, is really equivalent to display digital twin, right? That's where condition monitoring. That just needs deterministic, I'll call it machine learning. Performance prediction in statistical machine learning. To do the ones we are talking about, performance, understanding, and improvement, we need causal machine learning. And fortunately, that's all in hand. And I'll expose the details in the next few slides. Before we go to it, let me just terminology. Like I said, there are many different kinds of causal, and they work for certain type of data, not for other data. So when you make a statement about causality for IoT, there'll be a lot of people standing up and no, you don't know what you're talking about. So matter to be very careful. So I start calling this multi-channel IoT causal digital twin, or MIC digital twin. The whole point is that it is like this, the Rockwell's automation plant example I mentioned. So if you're thinking about measuring data, so this is one channel, maybe there is 2-3 channels here. There is a vibration, temperature, this thing, there is something else here. So these are all different sensors. So these are like all different channel data, and they're all measured simultaneously these days, wirelessly or wired. It's connected to some customer premises equipment and it comes back. So almost all the cases in IoT are multi-channel time series data. Now, the multi-channel time series data has some interesting things. See, even though maybe this is a connected system, let us say. So the data coming from here is really not, it's like looking through the straws. If you looked at only this, it is also related to this in somehow, but through this machinery and interaction, which we don't know completely. So it is important that, like in the global picture, we combine the information from all of these things to get the global picture of what's going on with this machinery. I can't quite tell what this one is doing here. Somebody in the audience would know. So that is kind of shown here. So each of these sensors are bringing information from different points on the plant, but they all have interrelated information. There are some things are causing others, and something are causing this, etc. So measurement at, let's say this is the current time data. So this is like time series. So it'll be like waving up and down. So the data at this point is related to data from the other sensor, data from the other sensor in the previous time, in the past. So there may be a transmission lag here. So the data here is affected by something that affected this a second ago. So those are all important. So these are all causal factors and causal relationships between these nodes. That is what MIC digital twin sucks out. And that is done through a model called SVAR, Structural Vector Autoregressive Model. I won't go into this. This is published multiple papers. The algorithms have been fully developed by others and have built on it. And they're very robust and stable at this time and can be applied to large number of sensor channels, and a big graph can be generated and so on. I'll show you some simple graphs from a practical machinery example in the next slide. So this is that example I was talking about. So NASA has a data set that I've made available to the public. This is like 4 bearings that is mounted on a shaft, which is driven by a motor, and loads are applied to some of the bearings and not to the others. And they monitored all these 4 bearings, that is vibration from these 4 bearings, from day 1 pristine condition to the day it turns out bearing 1 failed first after 14 days of continuous operation. And there's continuous data, 24 hours from each of these 4 bearings available for analysis. So that is what I would use to explain what's going on. So typically I kept talking causal graph in or DAG, directed acyclic graph. So a DAG for this system here would look like this. So there are 4 nodes, those are the bearings, and the connectivity between them, this is just randomly, just for illustration, drawn it. But when I analyze this data, let us say B1 is affected by B2 quite a bit. So there's a strong causal relationship. Weakly affected by B3, it has a weak relationship, etc. There is no causal relationship between B2 and B4, B2 and B4. Not clear in reality whether that'll be the case or not, but this is just made up. As an engineer, I always think, oh, this graph thing looks so abstract. I would like to see it more like an engineering diagram. These are the bearings, and now the idea is that these, when you perform that outcome analysis and what if analysis, we can actually physically see these are those causal weights. It's like knobs. You can turn it, and then you can see vibration coming from B1, B2, how they are affected each other, and so on. But it turns out not a lot of people use this, and it's a little clumsy for a couple of reasons. So what I have decided to do for this type of analysis is what I call fence causal graph. I needed to do this because of like I said, data from one node from a second ago may affect the current node. So you need time lag. So this is the current time, this is the previous time, and so on. So in this case, this is actually from this real data analyzed, if I remember correctly. So bearing 1 has a very strong coupling to bearing 2. Kind of makes sense. They're right next to each other. So if this is like out of whack, this would be out of whack a lot. So, or think of it as energy from B2 being dumped into B1. So maybe that's why B1 failed. We will see in the next slide. It also has past vibration from, let's see, B2 affecting it, or B4 affecting it. The dash green line is something called Granger causality, which we won't again talk about in this slide. So if you remember, this is the story, right? We are actually trying to look at data at each time, how the current and past vibration of other bearings are affecting each one of them. So all of them can be done simultaneously analysis during this with our SVAR algorithm. So on day 1, that is the pristine day, this big arrows, of course, are not part of the picture. There is very little causal connection. So another way to put it would be there is very little contribution of energy from one bearing to the other. There is some delayed something from B1 going to B2, or no, not delayed, current one. And there is something delayed and so on. So what I did was did this for day 1 to all the days up to the day it failed. I call it D day. And then you can kind of get a quick idea. So this is D day. This is when B1 failed. Its outer race broke or something. And this is the day before that, and so on. So without going into great detail, just by taking an upper level glance, you can see pristine, very few causal connections. And failure day lots of causal connections all over the place. B2 energy is just pouring into B1, and this is happening. Delayed energy, lots of them going here and there from B4 from 3 seconds ago. It's not 3 seconds, 3 samples ago, affecting B1 and so on. The day before, a little less. Now, clearly, this is not condition monitoring, right? You could just monitor the vibration of each of them and see B1 is increasing, and then someone can say, oh, go change that bearing. So that's not the point here. You would hardly use MIC digital twin and causal graph for condition monitoring. Now, this is for actually later on, the next slide, I'll show you an experiment where you can then ask some very interesting questions about this rather simple system and use that for improvement of the performance of this overall system. So this is the real big deal about causal digital twins. Yeah. I talked about you have that picture, you reduce it to mechanism, then you have knobs that you can tweak, etc. Think about a system where there are, like in this case, we have just 4 nodes. Let's say there's 100 nodes, and you can imagine there'll be so many connections between the graph. So if you think of the traditional kind of graph, there'll be so many links going back and forth and interacting and so on. So while it is nice to think and explain in terms of knobs tuning manually, that's really not very practical. So I've done an experiment where you actually do the optimization programmatically. So this is what we had on D-Day. So I asked myself a question. So this is one of those what-if analysis. What should the links in the fence grant link strings be on D-Day so that B1 is now operating like pristine on day 1, not like on D-Day. So on D-Day, what would make B1 perform like pristine day 1? What should the links be? So this whole graph can be put through an optimization program. And when I do that, this is the kind of result that you get. This is what the end result was. So the links, if the link weights were like this, link weights here meaning causal factors were like this, B1 on D-Day will look like it was on pristine. So this is the spectrum of the vibration of B1 on pristine. This was day 1. So mainly notice this big peak, spectral peak. So after this analysis, and when the optimization said this should be the link weights so that B1 operates like it is pristine, and the B1, and so I ran this network, so to speak, right? So you could get the B1 vibration data. Its spectrum looks very similar to this. There are some differences. It's missing some peaks here, but these are really not significant at this point. So this is what. So this was a what-if experiment. That now, if a machine dynamicist or expert came and said, "Oh, these weights," they could say, "Oh, this means we should probably put an extra coupling here so that the shaft does not transmit the vibration through that side, etc." So of course, it's a dynamic interaction between the domain expert and our digital twins. That's why I have that in my earlier picture. You saw domain expert is an integral partner, hand in hand with us. So this is the real power of causal digital twin. We'll be programmatically be able to determine how to optimize operations, and that increases productivity or reduces problems and so on and so forth. So all of these things are at hand, and we're ready to go run with it. So in summary, 2 quick summary slides. One is just to tell you that just to remind you that causality is our effort to reduce things to a mechanism. So this is nothing rare. This is the fundamental methodology of Western scientific method. It's called the Laplacian program. You just idealize away unknowns and randomness. Then you make a theory of it. Then you can use it, make them deterministic. This is what Newton did. Newton's second law, basically that ignored friction, ignored air currents, ignored this, You would get nowhere if you did. And then he came up with F equal to ma, second law, right? Force equal to mass times acceleration. So this is just a little Appalachian program. That's what is happening in causal analysis also. It's hard to understand because of, like I said, various schools of thought, various applicability. But if we focus on that MIC digital twin, multi-channel IoT causal digital twin, we can get far and solve this problem, and actually, more importantly, deliver real value to our end customers. And as we saw, counterfactual simulation, that is the essence. That's how you come to prescriptive analytics. Now, after this analysis, along with the domain expert, we could say, oh, add a coupling there, then this. That is what prescriptive analytics is, rather than saying this may fail, that may fail. Useful, but this is even more useful. So that tweaking of the mechanisms, that can be optimized and programmatically done, and you can do the root cause analysis. So just to recap, I won't read through all of this. So, but you can read through it at your leisure. So, what is digital twin? It's really a virtual working representation. What does it fundamentally do? It is really stitching together the local data to form the global picture, right? And why are we doing this? Because one, we want to monitor this remotely, and because we want to improve the performance. Now, those are the watchwords or the essence of digital transformation. So digital transformation that not everyone, companies, enterprise going through, in many cases, we'll be able to map it onto digital twin and then deploy those solutions. And digital twin solution is really a ladder of solutions, the display, the predictive, those two well known for at least this group of people, IoT, digital twin people. Prescriptive, much less known, but there are a few people who has an interest in it, and I have developed expertise in that area and happy to share it, probably through a kind of a, as a supplier to IoT SIs, system integrators. I'm happy to supply this technology. And how do we do it? And the achieving those improvement is through outcome analysis and root cause analysis that prescriptive digital twins allows us to do. And a very important part of it is the counterfactual simulations. Why it is counterfactual, etc. I didn't go into it, but we can talk about it another time. And how to actually implement this on as a software is on the IoT stack. This is probably a service that event driven for certain cases and on demand for other cases. So I hope you got a good general idea of what digital twin is, why it is important in digital transformation, and what causal digital twin brings, or MIC digital twin, multi-channel IoT digital twin brings. And what it brings is the possibility of prescribing performance improvement actions to our customers. Thank you very much.